Hey, College Math, welcome back. Here is our first section of chapter 6. Okay, chapter 6 is going to be about something called graph theory. Okay, and so our objectives are to define the parts of a graph and then draw some examples of graphs and describe their characteristics. Okay, so we're going to talk about graphs, but not in the sense that you're probably used to. Okay, so what does that mean? Let's start by looking at this definition right here. So a graph is our term here. A graph is a set of points called vertices connected by lines called edges. Okay, so an example of a graph would be if I just had three vertices connected like this. This is a graph. Right, and so it's different from probably what we're used to in terms of knowing what a graph looks like. We're probably used to x, y, axes, the coordinate plane, or even like a bar graph or like a line graph, right? That's kind of the stuff that we're used to. But that's not going to be the case for what we're going to talk about in this chapter. Okay, so in this little example I just drew, these dots right here are the vertices, and then these two lines right here are the edges. Okay, we'll definitely practice that here in a little bit. Okay, a few more words to talk about. An edge that starts and ends at the same vertex is called a loop. And then a graph is connected if there is a way to get from one vertex to all other vertices in the graph. Otherwise, the graph is disconnected, right? It's either connected or disconnected. So let's go ahead and let's just dive, oops, my bad. Let's dive right into an example. Okay, so first example, create a graph with vertices A, B, C, D, and edges AB, BB, BC, BC, AC, and CD. So the vertices tell you, okay, these are the dots that I want in my graph. So I have 1, 2, 3, 4 vertices that I want to draw. And you can just kind of do them in like a circle. So I can put A right here, B, C, D. I can also orient them in lots of different ways. It doesn't have to be here like in this little square format that I did or in like a circular fashion. It can be in any particular other way. Okay, so now I can label them. This is A, B, C, D. And this tells me what vertices to connect. So I'm going to connect A and B. That's what AB is. BB, so whenever you see that, that means that there's going to be a loop. So I'm going to actually erase this B so I can draw the loop there. I'll put B right here. Okay, so a loop kind of looks exactly like a loop. It's an edge going into and leaving the same vertex, right? BC, okay, and notice how there is two BCs. So that means I'm going to have two edges going from B to C, like so. AC, so from A to C, and then CD, so these two. And there's our graph. Okay, and so just to kind of describe this graph a little bit, what do we see here? We see that there are 4 vertices, 6 edges. Okay, and I can see that by either counting up all the lines that are connecting these vertices. A loop counts as one edge, right? And then I could also instead just count up how many edges that I was given here in the beginning of the problem. There were 6, right? And that matches up with how much there are. And if I take a look, oh, and then one last thing, there's one loop. Okay. One thing I want to see is if this graph is connected. The definition says if there is a way to get from one vertex to all the other vertices, sorry. So what that means is that if I can choose one vertex, and it doesn't matter which one you choose, is there a way to get to all the other vertices, right? So if I choose A as my starting point, am I able to get to every other vertex? Yes, I can go from A to B pretty simply, A to C pretty easily as well. I can't immediately go to D, but what I can do is I can go to C and then D, okay? It's okay if you visit more than one vertex to get to another one, right? So this graph is connected because if I can get from A to all the other vertices, then it makes sense backwards. I can get from all the other vertices to A, right? So this graph is connected. All right. Okay. Let's try another one. create a graph with vertices A, B, C, D, E, F, and edges A, B, that hold us straight there, right? So we'll read it right now in a little bit. Let me just draw the graph first. So I have 6 vertices. Okay, just kind of do them in this little fashion here. Again, doesn't really matter how you do it as long as you have all 6 vertices there. Draw them nice and big because then kind of get lost with the edges sometimes. And I'll actually make this a little bit thinner. Okay. So then label it A, B, C, D, E, and F. And then I can connect all my, or I can create all my edges. So AB, BC, CA, so A and C get connected, like so. AE, BE, CE, DD, so a loop at D, DF, and then FF, so a loop at F. Okay, and there is our graph. So now let's describe it. There are 6 vertices, 9 edges. And then is this graph connected? Okay, well, I can just pick a vertex. Let's start at B. Can I get to every single vertex from B? I can go to C, I can go to E, I can go to A. But if you notice, there is actually no way that I can get to D and F, right? And so one thing to know is that you can't really jump. For example, you can't like jump highways, right? I'm on a highway right now. I can't just jump onto this highway right here, this other edge. Okay, so I can't go from edge to edge. If I leave a vertex, I have to go straight to another vertex using that edge, right? So I can't just do that, right? That would not be allowed unless there was a vertex right there. Okay, but there isn't, right? So this graph actually is not connected because there's no way I can get from B to D. The only thing leading into D is itself and F, and the only thing leading into F is itself and D, right? So there's no way that this graph is connected. This one is disconnected. Okay, cool. So you're probably wondering, as of right now, what is the point? What are we doing? Why are we just drawing a bunch of dots and lines connected to each other? This has a lot of application to kind of like networks, okay? Kind of networking systems. You can think of a network like a social network, like social media, but you can also think like more physical, like a metro network. If any of you guys are from Phoenix or have been to Phoenix, there's the thing called the metro, and that kind of takes you from place to place. It's connected to lots of different places, or just even thinking of the city bus. So I call it metro, the light rail, right? Sorry, I think it has the word metro, and I haven't been there in a bit. But the light rail, it takes you to lots of different places. Thinking about airplanes, airplanes have routes from one city to another that can be represented by a graph, right? I can make all the cities dots and all the airplane routes edges. Okay, so this has a really good applications into like a lot of things in our life, and we'll talk about that a lot as we kind of go through this chapter. Okay, so a little bit more vocab. We have the order of a graph. So order is the number of vertices in the graph. The degree of a vertex is the number of edges connecting to that vertex. A path is a sequence of vertices and edges that leads from one vertex to another without repeating an edge, right? So think of like a path like that you walk, a trail. A circuit is a path that starts and ends at the same vertex, so ending where you began, right? And then a bridge is an edge in a connected graph that would disconnect the graph if it was removed, okay? So if I take away that bridge, now I have 2 land masses that are no longer connected, unless there are other bridges, right? Okay, so sorry, I keep forgetting that I have to click on this to move. So those are a few more vocab terms. Let's go ahead and see about those here in this graph, okay? So answer the following questions about this graph below. We have A, B, C, D, E, F. We have 6 vertices. And we kind of just answered the question part A with that, right? What is the order of the graph? That is the number of vertices, so 6. Okay, so we have order just plain old 6. Okay, what are the degrees of A and F? Okay, remember degree, that means how many edges are going into that vertex. Let's start with A. I have 1, I kind of misdrew it here, but there's 2 right here. 2, 3, and then 4. So the degree of A is 4, and this is how we write it. We write DEG of A is whatever the degree is, 4. And then for F, we can kind of see it right here. There's only one edge going into F. So DEG of F is 1. Okay. Part C lists 2 different paths. Okay, so a path, you can start at any vertex you want. Let's say that I'm going to make a path from C. Okay, so one path could be from C to B to E. Okay, that's a sequence of edges and vertices that do not repeat the same edge. Okay, I don't need to start where I began. I just need to start at the vertex that I start and then end somewhere, right? And it has to be at least 2 edges. So from C to B, B to E. That's one path. C, B, E. And then another path, I can start at a completely different vertex. I can start at F. I can go from F to E to B to D. It can be more than just 3, right? The only stipulations are that you don't use the same edge more than once, okay? So F, E, B, D is another potential path. F, E, B, D. Okay, now let's 2 different circuits. Now in this case, we want to end where we start. Okay, so let's say I picked D. One circuit could be D, B, E, D. So D, B, E, D is a vertex, right? Or a circuit, sorry. And you know it's a circuit because it starts and ends with the same vertex. All right, one last circuit to find. Let's go ahead and start maybe at like E. I can go E, B, A, C, E. E, B, A, C, E. Okay, E, B, A, C, oops, E. Okay, 2 different circuits and then 2 different sizes, right? Just like with the path, I can find different size paths. Okay, now the last one, does the graph contain a bridge? If so, identify it. Okay, take a look at the graph. Is there any edge here that if I were to get rid of that edge, my graph would now be disconnected? It doesn't really look like there is, but we can kind of, if you can maybe see it, EF, this edge right here is a bridge, because if I were to get rid of it, okay, remember the criteria is that my graph becomes disconnected. And it does, because now there is no way to get from B to F or from A to F or any other vertex to F, right? Sometimes, you know, if a vertex is standing alone, it's still part of the graph, right? But now we can tell that there's no way to get to it, so my graph is disconnected, right? So that means that EF is a bridge. So let's go ahead and write that down. So our bridge is the edge EF. All right. And there's our video on graph theory, right? Just a little bit of an introduction, just to kind of, you know, put things, give us a little bit of a foundation, right? So again, graph is just a bunch of dots connected with lines. Connect the dots, right? And like I said, it has some pretty nice applications, especially, you know, I mentioned like metro, subway, airplanes, social media networks. It could also be used in computers, right? Kind of networks inside of computers. And like I said, we'll talk about a lot of that stuff within the next few days when we go through this chapter. Okay. Have a good rest of your day. I will see you in the next one.